So welcome everyone to Cryptography 201. I know for a lot of you, it's your first workshop today and it's your first time joining a live workshop. And for those of you joining the live workshop for the first time today, my name is Samin and I'm going to lead the workshop. And we're going to talk about Cryptography 201 and it's going to build on the concepts that we discussed in Cryptography 101. Also, when you join, there should have been a link shared in the welcome box, and that link includes some resources that we will be discussing today. It also has a script on the first two slides that I will be using to solve a problem, just so that you have it. Another important thing, so when I'm solving some of the challenges live, it's really important that you try to engage with me and try to pay attention to how I'm solving it. And then when you go back and then you try to attempt it on your own. But if you try to solve those challenges at the same time I'm solving them, it might be a little bit confusing to switch back and forth between screens. So I recommend that while I'm solving the challenges, that you just watch along and participate. And then at your own time, you try solving the challenge again and see if you're able to attempt it. Also, we have today we have Madison Henry, who and she's always here, and she's going to be helping with any technical issues that you guys might have. So if there's any technical issues that you're experiencing, please send a message to Madison. Okay, so let's get started. So today we are going to talk about a little bit of Cryptography 101 and just a short review. We're going to do some warm-up challenges, then we're going to talk about symmetric encryption and then two of the popular crypto systems, DES and AES, which are symmetric algorithms, and we're going to talk about asymmetric encryption and then RSA, and then we're going to do a wrap-up, and we're going to also solve a lot of challenges today. Today, if you do want to follow along, we will be using the web shell that's available at picoctf.org or 2019game.picoctf.com. So we talked about the importance of cryptography in the 101 workshop and what really cryptography provides. And the first thing that cryptography provides to everyone is confidentiality. That means that it ensures that data can only be seen by the intended recipients of that data. For example, you have medical data, which is very confidential. You don't want everybody else to see it. To make sure that medical data is protected, organizations encrypt it before storing it. They use an algorithm to conceal what it actually says. So it changes the form of it so that it wouldn't be, easily be readable by someone who doesn't have the key to decrypt that data. Integrity is to ensure that the data that has been received has not been altered or tampered with. And we talked about how hashing helps with, confirming integrity, because when you form a hash for a document, a file, or anything, if you were to change anything else in that document, the hash value would change, and then you would know that this has lost its integrity because it's not the same, it's been altered. Non-repudiation, to make sure that the person who is sending that data really did send the data and it's not somebody else. And then authentication as well, to prove one's identity. So cryptography is really important in the space of cybersecurity, especially in terms of confidentiality. It allows us to share messages and, share data in a confidential manner. So let's talk about some important terms that we will be discussing, and it's important to know these terms. So plain text. Plain text is original text in its original form. It's readable by humans. It's something that we can understand. So plain text would be something like hello. Ciphertext is text after it has been encrypted. So if we took the plain text hello and we applied, for example, we talked about Caesar cipher last time, we applied the Caesar cipher to it, the result of that would be the ciphertext, which we wouldn't know what it is unless we knew the key to decrypt that. Cipher is an algorithm or technique for performing encryption or decryption. And encryption is the process of converting plain text into ciphertext. So when we're going to take that hello message and encrypt it, or we want it to hide the meaning of it, we're going to do encryption on it. And then when we want to uncover the meaning of that, what it means, we're going to do decryption on it, which is the process of converting ciphertext back into plain text. So keys. So keys are a string used in combination with a cipher, which is also known as an encryption algorithm, to transform plain text into ciphertext. Without knowing the key, ciphertext cannot be converted back into plain text. And we discussed the importance of keys the keys of a crypto system are really what provide it with that confidentiality. If anybody else knows the keys, then there's no point of having that crypto system because, or sharing that message, because then anybody else can decrypt your message if they have your key and read it. So there's no more confidentiality there anymore. So we talked about the importance of keys. We also talked about the key space, which is the number of possible keys that can be created from an algorithm. The larger the key space that an algorithm has, the more secure the algorithm is. Of course, there is a drawback, or there is a trade-off with that, because the more key space, or the larger the key space, the longer it takes to encrypt or decrypt that. So you have to find the right balance. So let's take a look at encryption algorithms. So we have what's are known as block ciphers and stream ciphers. Block cipher is when encryption happens on a block of data. So you just have that chunk of data and it happens on that entire block. So we have algorithms like DES, triple DES, AES, that are block data ciphers. And then we have stream ciphers where a single bit of data is encrypted at a time. And these tend to be, there's RC4, seal are just some of them. What's really important in encryption is to understand Kirchhoff's principle, which is the theory that the security of a crypto system must lie in the choice of its keys only. That means that the keys must be protected and private. Everything else, including the algorithm, is public knowledge. So the only thing that's not public knowledge is the keys. You have to protect your keys because that's how somebody can, like when you have your house key, you have to protect the house, right? People can know where you live, people can know what your house looks like, but they can't have access to your key. Once they have access to your key, they can unlock the door and get in. And that's just how it works with crypto systems. If they have access to your key, they can use that key to decrypt your data and figure out what it says. So what exactly is an encryption algorithm? So an encryption algorithm is a mathematical formula used to transform data into meaningless ciphertext. And you use protocols and algorithms. They are widely used and heavily analyzed, and they have been accepted as secure and as the industry standard. If anybody tells you that they have their own proprietary crypto system, then it's probably not a good idea, because these crypto systems have been tested by cryptanalysis. They've been, they've brute forced them, they've tried to break them, and they've been proven to be secure crypto systems. There's a lot of research behind them to back them up. The longer the key size, the harder it is to brute force. However, the larger the key size, the more computing power is required, and it could take longer. So common encryption algorithms use are DES, AES in 128, 192, and 256 bits in key size. The longer the key size, the more secure the crypto system. And there's also RSA, which is an asymmetric encryption algorithm. So this is an example of what an encryption algorithm looks like. So you have data and it performs mathematical functions on it. As you can see, it's performing different mathematical functions. It's shifting the data around. In the end, what you have is data that's not easily readable without a key. And the key is mathematically related to the algorithm, and it's needed to unlock the text to discover what the message truly was. So this is encryption happening right here, and right over here we have decryption happening. So again, let's take a look at how this works. So you're going to take plain text and you're going to apply an algorithm to it, an encryption algorithm, and what that results in is a ciphertext. And to take that ciphertext and decrypt that message, you're going to have what's known as, you're going to use the key, and you're going to decrypt that ciphertext into plain text by using the key. So the key is key here, and that's a pun, but that's it. It's really important to know that the key really holds the crypto system together. It's really vital to protect the keys and to make sure that they remain secret and protected. Let's talk about encoding versus encryption, because oftentimes the two of them are confused. So encoding is the transformation of data from one form to another. And it's for useful transmission of data and efficient storage of data. So the data, you transform it in a different format, but you don't need a key to decrypt that data. Anybody can shift that data back into its original form. So you're not trying to hide anything when you're encoding a message. However, when you're encrypting a message, you're trying to, add confidentiality. So you're trying to actually conceal the true message. An example of encoding is converting hexadecimal to ASCII, or converting a message into Morse code because there's no key. An example of encryption would be taking a message and encrypting it using an AES algorithm with a key. So encryption is the transformation of data from one form to another, just like encoding, but an encryption algorithm is used alongside a key. And if the key is unknown, the message cannot be reversed. So let's do a warm up, and we're going to take a look at some problems. So let's take a look at this problem right here. And so you can use your own machine to solve it, or you can use the shell. Let's try solving this with the shell, which is provided on picoctf.com or 2019game.picoctf.com. So you're going to be asked to provide your username and your password. And I have a long password, just sometimes frustrating. So let's just clear all of this up so we have a nice and clear view. So let's look at, let's paste that, and we're connecting to this port on this site, Netcat. We're using Netcat to do that. So this is our encrypted message. Can anyone, just from our Cryptography 101 and just from a little bit about what we discussed today, does anybody know how to approach this problem? You could feel free to type in the chat box below. Any ideas on how to approach this problem? Okay, let's just copy and paste this. To me, it looks like this is a substitution cipher. It clearly looks like, things are being substituted, text is being substituted for another. And if I look closely, I could see that this section right here is probably going to be the flag because of these tags and knowing the flag format. And it looks like it's going to be substitution cipher. So what I can do is try to find a substitution cipher decoder. Let's try using this. Let's just paste that into here and decrypt that. I'm not sure why that is not working. Let's try this website right here. It might need the whole message to analyze it better, so let's copy the whole message. Let's see what happens. Let's go back to the first website. Hopefully this works. If not, I have no idea why it's not working. Sometimes live demos tend to fail, which can be frustrating. So it's just analyzing what substitution is taking place. And it's not, and let me just check my notes and why it's not working. Was that the website I used? Okay, so it's probably not a substitution cipher because it's not able to detect that. Let's look at Vinir cipher decoder and check if it's that. Okay, let's plug it in. See if that works. Decode. Let's see if it is. Okay, we're going to come back to this problem because I'm not sure why it's not working. Let's go back to the problem and read it again. Yeah, let's come back to this problem at the end. Maybe I'll remember how I solved it, but I'm pretty sure it's a Vinir cipher. So let's not worry about that problem. Let's try tapping. Let's connect to the shell. Let's clear that to make it more easier to read, and let's connect to this port using Netcat. Okay, so does anybody have an idea of what this is? Let's look at the hints. What kind of encoding uses dashes and dots, and the flag is in the format picoctf? So what I would do, how I would approach it is I would do dashes and dots, encoding, and see what comes up. And I see Morse code, so I'm going to try to find a Morse code decoder. Morse code decoder. And let's use this one right here. Let's just paste that. Oops, that's not what is supposed to happen. C, Morse code. So there is our flag right over here. We would probably need to convert this back into these brackets, but that's our flag right there. So it looks like Morse code. So these challenges are not too bad, right? Let's try Mr. Worldwide and see what that comes up with. I want you guys to try this on your own, but I would love if anyone could tell me how they would solve this problem. Let's take a look at this message right here. So does anybody know how this problem would be solved? Looking at this, what do these look like? Does anybody know? Feel free to let me know in the chat box what you think this looks like. So nobody has an idea of what we could use to solve this. I'm just gonna ask, I'm just making sure that the chat box is open because I don't see any engagements, which is weird. So let's just make sure. Okay, so I see people engaging in the Q&A section, and somebody has said coordinates, and that is correct. These look like location coordinates. So how we could probably solve this problem is by taking these coordinates and these look like longitude, latitude coordinates, and plugging them into a map and seeing what the result is. So I'm going to leave this problem with you guys to solve. But a lot of the cryptography challenges, you're going to have to kind of, figure out what's taking place and try to solve it and see what's happening. And it might not be like an encryption algorithm. It might just be different forms of encoding, like longitude, latitude. And one of the problems, they give you pictures of nautical flags, and you have to try to decode those flags. So I guess I'm just not able to see the chat then because, yeah, so I'm not able to see your messages, which is strange. So in my chat box, I cannot see everybody's messages, but I can see the Q&A. Okay, so I'll just go through it. I will just go through it with everyone because some people want me to solve this. So let's just try solving this. I'll give you guys a hint. Okay, so let's look at GPS coordinates. So we could put that value right here, and we're gonna get what we get when we put that address. Get address, get altitude. Okay, let's use Google Maps for this one because this one doesn't seem right. Google Maps, and let's see if we can paste those coordinates and look it up. Okay, so this coordinate looks like it's going to be Japan, or let me try flipping the coordinates the other way because I remember it was something else when I solved it. So the first one is Japan. Because of my screen sharing, it gives me a hard time when I switch screens, which is really frustrating. Let me try copying and pasting it right there. So the first one would be Japan. See what the next one is. The next one is in Ukraine. So how you solve this problem is what ends up happening is you have to take the cities or the countries, and you just take the first letter of each country and you put it together, and that's how you're able to solve this problem. But I don't think it's detecting the latitude and longitude correctly because this is not what it was. This is not how the order was. So that's the hint to solving this problem. So that's one of the problems. Let's take a look at flags just as a hint, just as another challenge. So for this one, what I did was Google Maps, nautical flags, decoder, images. And so I looked at a key like this and saw what each flag represented to solve the problem. So just trying to demonstrate to you guys that it's not always going to be it's not always going to be the like in encryption algorithm. It's going to be like different forms, and they're going to want you to get creative with it. So your best bet in these type of challenges is Google, because it could be anything. Like, we don't know what it could be. Like, it could be like cereal boxes, or just as an example, it could be anything. It could be very random. So you just, Google's your best friend with cryptography problems when they're not using an encryption algorithm. And so, yes, so if you type a chat message to all panelists, I'm able to see it. So maybe everybody try using all panelists to send us a message. Then we might be able to see it better. So let's get back to our challenges. And so those were some warm-up challenges. I do know how to solve this problem right here. And there was a link, and I used this link because the problem is with the veneer cipher, you need a key, and we didn't have a key. So what this link does is it allows us to figure the key out. So let's plug in what we had before, clear this up, and let's go to my cat right here. And the screen sharing thing is really annoying me right now. Let's paste that into here. Let's copy and paste this into the solver, and it should work. It worked when I tried it. Break cipher. Okay, so it worked finally. And the key that the veneer cipher was using was flag. We didn't know that key, so it would have been hard to solve, but using this veneer solver, we were able to do it. And so the key, the flag is somewhere in here. It's right here. Pico CTF right there. Okay, so somebody wants me to solve flags, so let's solve flags. So this is flags. I can't type in on this, but that's okay. Let's just use our shell to type. So let's go back to here and let's look up google.ca. It's easier to go to Google Nautical, flags, alphabet, and let's look at images and find one that has like alphanumeric. So this one looks like it has all of this one, no, it doesn't. Key is to find a nice flag that has all of okay, this one looks good. This one looks like it has all of them. So let's take a look. So our first flag is a blue and white, and we probably know that's going to be P, and it is P right here, because we have, so we don't need to solve this. We know this is going to be in the form of Pico CTF. This, because this is F, this will also probably be F. Let's confirm if this red triangular, yep, this is F. Let's look at a flag for red, yellow, red, and then yellow in between. So this is going to be 1. Then let's look for a flag that looks like this. To me, that would be A. So right now we have F1A. This looks like it's going to be, where is it? Yellow and blue. Let's see, G. So this is probably going to be S or something, or 5 maybe. I'm pretty sure, yep, it's 5. It's going to be 5 because it's going to spell out flags. And then this is going to be A. This is going to be N. So we have flags and this is probably going to be D. Yep, this is D. This is going to be flags and 5. Which one? What is this one going to be? Red, white, blue. Red, white, blue is going to be T. Flags and T. This is going to be U, T, U, F, F. That's the flag. So that's how you would solve it. The trick part is that you have to find one with the numerics as well, because some of them are using some numerical values and not just alphabetical values, but that's how you would solve flags. So those are some of the warm-up problems. And you saw that not all of them are using symmetric or asymmetric or encryption algorithms. They're just using you kind of had to solve a puzzle in a way and use some Googling skills. So those challenges are always fun because you don't have to think too deep. You can just Google it and hopefully the solution is right there. I'm gonna enable the chat. And now I can see the chat box. I could see the chats when you guys send to all panelists. So thank you for solving that. Okay, let's talk about symmetric encryption. We talked about the importance of keys, right? So in symmetric encryption, one key is used to encrypt the plain text and decrypt that as well. So you really have to protect that key. The key is shared among the receiver and sender of the data. The key cannot be made public. The key must be protected, and examples of symmetric encryption are the Caesar cipher, AES, DES, triple DES. So in this scenario, the key is only known to the sender and the receiver. If I was to be sending you guys a message, you would all have the key and I would have the key, and we would know the key, but somebody else cannot know the key. If they know the key, then they can decrypt our message. So, and then that there's no point of then having, using that key anymore. We have to change our key once somebody found out what it was. So let's look at one of the most popular symmetric encryption algorithm, DES, which is outdated now. So DES stands for Data Encryption Standard, and it was created in 1974 by IBM and adopted by NIST. So right here we have exactly what would happen in original DES. However, it was discovered over time that DES was weak because it could be cracked easily and the 56-bit key was too short. There's a famous quote that solved this DES problem. The only solution here is to pick an algorithm with a longer key. There isn't enough silicon in the galaxy or enough times before the sun burns out to brute force triple DES. So then triple DES was introduced, which is now used widely. And triple DES is way more secure than DES, and triple DES applies the DES cipher 3 times. So it's super secure. It doesn't have the problem of being able to be easily brute force like DES did. So that's the new, like DES is outdated, but now we have triple DES. We also have AES, which stands for Advanced Encryption Standard. AES encryption has 3 different block ciphers. And remember that AES is a block cipher, so encryption happens on a block of data. So we have AES 128, which it happens on 128 bits of data, AES 192, and AES 256. Obviously, 256 is most secure. So these block ciphers are named after the key length they use for encryption and decryption. All these cipher encrypt and decrypt the data in 128-bit blocks, but they use different sizes of cryptographic keys. So the keys can be, the longer the key, the more secure your crypto system is. So since the algorithm AES is considered secure, it is a worldwide standard, and there are 3 options for encryption key lengths: 128, 192, or 256 bits. A lot of services like, password managers or email, they use AES because it's a standard and you might see it being used widely. So it's important to be aware that this is one of the most popular encryption algorithms. It is a symmetric encryption algorithm. So just a reminder that just because I'm seeing the chat, that your flags might not, your CTF flags might not be the same as how I'm solving them, because there are different variants of it. So it's important that you solve the problem on your own to figure out exactly what the flag is, to use your especially for the flags problem, to use your specific image that they provide, because they have different flags for the different problems. So my flag might not work for you. So now let's talk about asymmetric encryption. So in symmetric encryption, we had the same key that was shared between the receiver and the sender of the data. But in asymmetric encryption, we have 2 keys. We have a key pair. And asymmetric encryption is also known as public key cryptography, and it involves a key pair that is mathematically connected and works in conjunction with each other. So we have our private key and our public key pair. The sender uses the receiver's public key to encrypt the data, and the private key is used by the receiver to decrypt the message. So basically how this works is that your public key, let's say I want to securely exchange information between us. So I want you guys to be able to send me confidential information that only I can read. So what happens in this scenario is that I will have a public key and you will have access to my public key. You are going to use my public key to encrypt the message you want to send to me. When you send that message to me, I will be able to decrypt that, because the keys are mathematically correlated. They link somehow, and that's just the beauty of math, that they're related. So only I will be able to decrypt the message you are sending me using my private key. Whoever has the private key can decrypt the message. So it's my responsibility to ensure that I protect that private key and only I have access to it, so that I can securely exchange, so that you can securely exchange your data with me. And you can look at this, an example would be a mailbox. So we all have access to those mailboxes, right? We can look at those as the public key. When we want to send information, we can put that in through those slots. However, only the mailman can come and unlock it and take that message out, because they have that they have the private key, and we have the public key, which is the slot. That really helped me to understand this concept of asymmetric encryption better when I was studying it. So let's take a look at one of the most popular asymmetric encryption algorithms, known as RSA. And RSA was founded by Ron Ribis, Adi Shamir, and Leonard Adelman, and their last names make up RSA. So Ribis, Shamir, Adelman, they're the inventors of RSA. And in 1977, they publicly described the algorithm. And it's a public key algorithm that is used for key establishment and the generation and verification of digital signatures. And it's a standard. It's still being used. It's such a powerful crypto system, very strong. So this crypto system relies on the fact that on selecting two very large prime numbers, P and Q. If somebody has these P and Q, then you are vulnerable to attack. So the beauty of the RSA is that it works knowing that when you select very large prime numbers for a large product, so the way it works is you multiply two numbers to create n, and that n is your public key. And then you have the totient such that the totient is equal to p minus 1 times q minus 1, and you choose a number e such, and this math can be hard, and if you don't understand it, it's okay. It's just important to remember the formulas to be able to solve RSA challenges that we're going to be doing a demo of in just a bit. So choose a number e such that e is greater than 1, but e is less than this totient value right here. And your total public key is made up of this n value and this e value. And then you have your d, which is your private key. And d is the totient plus 1 over e. And that's your private key. So your total private key is n and d. So n are the common things between these two. To send a message m, which is we're calling the message m, the person needs to calculate x, which is message raised to that to the e, which is part of your public key, modular n. And we're going to talk about mod in just a bit. And if you're familiar with Python, then you've probably heard of the modulus operator. And then they're going to send that x to you, which is the decrypted message. If you want to encrypt it, you have to calculate x raised to the power of d mod n. This will give you back the original message. The best way to use this algorithm is for the other person to sign the message with your public key and his own public key to ensure authenticity and encryption. And these are taken from picoctf.org, this explanation, their primer, which is why it's really important that everybody reviews the picoctf primer that's available on their website. So let's do like a mathematical example. So we have a public key, a pair of numbers e and n, and we have a private key, which is a pair of numbers d and n. We have your message, we have your ciphertext. To encrypt the message, you're going to take that message, raise it to e to the power of e, and then do modulus n, and you're going to get your ciphertext. To decrypt and get back this original message, you're going to take the ciphertext, raise it to the power of d, which is your private key, modular n, and you're going to get the message. So let's take a look at this example. So we have 11,117 as your public key, e and n, and we have your private key, 35 and 117. And if we want to, solve and we want to encrypt this message, we're going to do the message to the power of e, which is 11 mod n, and n is 117. So to solve that in Python, we're going to go back to our shell just to show you how to solve it. Let's clear this up. Let's open up Python. Actually, let me clear this whole screen so that it's easier to read. Let's open up Python. To solve this challenge right here, this is not a challenge, but to solve this mathematical equation, how you would do it in Python is, so it's 10 to the power of 11 mod n. So we would do 10 to the power of 11, and for modulus, we use the number sign, 117, and we should get 82. And so our answer is 82. So that's how you would solve if you had a mathematical problem like this in using Python. And then for decrypting, you would do 82 to the power of 35d, remember, and then mod n, and we would get our original message that we sent, which was 10. So the encryption formula is right here, and the decryption formula is right here. So now that we know this and we know how RSA works, we're going to solve a tricky, one of the more trickier challenges. And I had to do this a few times myself to really get the hang of it. So just try and watch and try to see what's going on. And then after I solve it, and when you go back on your own, then try to solve it again. This challenge is a little bit frustrating because it times you out if you take too long to answer it and if you take too long to solve it. So it's okay to record those values and make sure you're able to solve them. And I've noticed that it doesn't give you different values each time. So if you keep those in the notepad, then you can save them and then repaste those values in to make it easier to solve the challenge. So you can use, so the challenge we're going to be solving is the RSA pop quiz. We're going to connect using this right here. You can use this shell to connect. All you would do is use netcat, connect to the port right here, and the problem would start. I'm just going to make it easier for us to follow along. I'm going to use this web shell that I have on my machine, but you can feel free to use that web shell that's provided on PicoCTF. It functions the same way. This one just doesn't time out as fast, which is why I'm using it to be able to demonstrate it to you guys well. So let's hit enter. So good morning, class. It's me, Miss Edelman Shamira Revis. Today we'll be taking a pop quiz, so I hope you studied. Cramming just will not do. You will need to tell me if each example is possible given your extensive crypto knowledge. Inputs and outputs are in decimal, no hex here. So can we find n given our Q and P values? Anybody remember from what we just discussed if we would be able to find n given these values? Yes, that's correct. We would be able to because n is the product of Q and P. So you can do this in Python, but I'm just gonna calculate it so I don't switch tabs too much. And so we get this large number when we multiply it, 4, 6, 3, 6, 8, 7, 8, 9, 8, 9. And now it's going to give us another problem. It's going to say, we're given our P and N, can we produce Q? And we can produce Q because N is equal to P times Q. So Q would just be N divided by P, right? So we can solve this problem. So let's do that. Let's do that value of N divided by P, and we would get 93089. Outstanding. Okay, so now we're given N, which is a large number, and we're given E, and we're asked to produce P and Q. Is this possible? Now, if we remember when we're coming up with our keys and when we have the RSA algorithm, we are to choose two large prime numbers, Q and P, that are their product gives us N. So this kind of shows us the power of the system because it would be very hard to figure out the two numbers that were used to give us this huge number. Obviously, using a computer, it might be able to solve it over time, but this is just a very hard challenge to solve like that. So this problem is not feasible to solve, so I'm going to say no. So the next is totient. Can we produce the totient given our Q and P values? We can, because totient was P minus 1 times Q minus 1. So we're going to do 66346 because 66347 minus 1 is 66346 times 12610. And it just timed me out, but as you saw, so that's the annoying thing of the challenge, is it times you out if you're not fast enough to solve it. But let's just quickly go through these. Let's just copy and paste these values quickly. It doesn't time us out. That's why this is a super frustrating challenge, because you'll be in the middle of solving it and it'll just time you out. That's why it's important to make sure you keep your 93089, 93089. This was not possible. This is possible, and I calculated the value. It was 836623060. Now, can we find the ciphertext using plain text EN? Yes, we can, because the ciphertext is plain text raised to the power of E modular N. So let's copy that. Copy that. Let's open another window, and let's go into Python to solve it. And so we have that huge value raised to the power of 3 modular, and that N. I really hope that this does not time me out. So we're going to copy selection and paste it, paste selection right here. And this is the value that we get right here. We're going to copy that. We're going to go back here and paste it and hit enter. So it's given us the ciphertext EN, and it's asking us if we can reproduce the plain text. But to decrypt the ciphertext, we need the decryption key, which was D, and we don't have D, so this is not possible. Now it's asking us if it's possible to produce D, and it is. And for this, I'm going to run this problem so we get to the end, and then I will explain exactly what I did. But I used a script. I ran a script, and I'm going to share it. And that was a script that I shared with you guys. Just so we get to the end of this problem, then we can talk about what we did. And we're going to copy that. And I'm going to hit yes. And then it's given us P, C, E, N. And because we have N, we can solve, and P, we can solve for Q. And because we have that, then we can solve for D as well, because we have the ciphertext and everything we need to solve for D and Q. So this is possible. Again, for this one, I use the script, and I'm just going to run it so that, and this is the value that we get. And I'm going to explain the script in just a bit after. I just want to make sure that we don't time out of this problem. And we timed out of this problem, which is why it's super frustrating. Okay, so after you get that value, so we won't run the problem again because it's, so you're going to get this value. Oops. You're going to get this value right here. That's the final. And it's going to ask you in the end to decrypt this value, to convert this value from hex to ASCII to get the flag. So let's go back into right here. We go to Google, and we're gonna go hex to ASCII. Sorry, decimal to hex first, decimal to hex, that's a decimal number. And then we're gonna convert that, didn't copy, and paste that into here, convert, and that's our hex number. And then we're gonna do hex to ASCII and paste that, convert that, and that's going to be our flag, but it might be different. Everyone has different values, so it's going to be different. So let's talk about, let's go back here and talk about how we were able to solve for D. So let's take a look back at our problem. So to solve for D, we know that we would need our ciphertext, we would need our N, and we need our original message because we have this formula. So we could solve for D with all of this given to us, right? Because we had our ciphertext, we had our N, we had our message, and we had all of this. We just needed to solve for D. So let's go back, and we were given all of that right here. And we had our P, our Q. Given our P and Q, we could solve for N. and then we have our exponent, and then we could solve for D. So let me show you guys the script that I use, and I've shared that with you as well. So let's take a look at the mod d.py. So this is the script that I used, and you would plug in your Q, P, E values, and it's just going to calculate the modular inverse E, and P minus 1 times Q minus 1, that's the quotient value, and you're going to end up with your value of D. So that's the first script that I use to solve for D. So let's exit out of here. Let's take a look at the script that I used to solve the other problem, which was we had our P, a ciphertext, E, N, and we just needed our plain text. So we have our N and P, which means we can solve for Q, and we have our ciphertext as well. And we need to find the plain text. Let's go back to this. So to remember, for plain text, you need your ciphertext, you need your D, modular of N, which is going to give us our plain text. And we had all of that, and we just needed D. So what this script would do is that it solves for D. First it solves for D, and then it solves for the plain text after solving for D. So that's exactly what the script does. It's okay if you don't understand exactly like how the script works, but it's important to note that this problem showed up in 2018 and it showed up again in 2019, and there was no variation between the problems, so it's pretty consistent. And I have a strong feeling it might show up again because it is a little bit challenging, but it would really be helpful to keep these scripts, which were shared in the welcome box at the beginning. So when you solve that and you get your plain text, you convert that decimal to hex and then to ASCII to get your flag. I encourage you to try this problem. And I've given the script, so try creating the script. So let me just show you. You would do that in the web shell. It's the exact same process to create. So see, the problem would be solved here. Let's go back, clear this, and to create a script, you would name it whatever you want, .py, and then you would just, I already have that script here, but you would just paste that script into here, the script that I've given you, and then you would save that, and then you would Python mod.py to run it, and it would give you the value. So that's how you would use that in the web shell server. For this problem, I recommend having 2 shell servers open and making sure you save all of these values in the notepad because it can get tricky. So we talked about RSA. And so that was it for today. It was short and simple. We solved a lot of problems. Here are some resources that were also shared. The scripts are available. I gave the scripts, but if you want to create your own scripts and you want to understand the math of it, it uses something known as the Euclidean algorithm, and you can read more about that in this link, as well as when you read more about the RSA algorithm. And here's a good breakdown of the RSA cryptography algorithm if you want more details. Here's some online tools that we use for encrypting, decrypting in different algorithms and different ciphers. So that is it for today. Thank you for your time. And next week we're going to be covering Digital Forensics 201. And if you have any questions at this time, please feel free to answer and ask them. And if you don't have any questions, please feel free to leave and enjoy the rest of your evening. Mini RSA would be solved using a script that you could find online. So the recent mini RSA, you just look up the script for it, and you just take the script, you plug in your numbers, and it'll solve it for you. So that's not too bad. Thank you guys. Please feel free to leave or ask any questions, and make sure to try solving these problems that we did on your own. And we all have a different different flags, and there's multiple different ways to solve a problem. So if you find something that you understand better, feel free to use that method as well. What are the variables from that cipher DPQ? Yeah, so let's go back and look at the variables. So your D is your decryption key, your E is your encryption key, your P is the P and the Q are the two large prime numbers that you select, and the product of that is N. So you need the P and Q to solve for N, and E and N make up the public key pair, and then the private key is D and N. So that's what's important to have the P and Q, because P times Q is equal to N, if that makes sense. Hope that answers the question. But yeah, guys, have fun with the challenges. And I did share last time. I'll share this again for those of you that are still here. Let me go back to exit. Martin Carr, Pico CTF. So this is the YouTube channel for the professor from Pico CTF. And he solved all of the challenges from 2019 as well as some of the 2020 ones. All the solutions are here. And sometimes he might not use the same technique that I use, or I might not use the same technique that he uses. And then there's other people as well solving these challenges. So there's so many different ways to solve a challenge. And if you're stuck with one way, you could try using another way to make it easier to understand. So yeah, if you don't have any more questions,